Okay, hi, I'm Olivia and I'm a master's student at Keele University. Today I will be taking you through my master's thesis, which is the origin and paleoglaciological significance of Herefordshire Ice Age ponds. Next slide. So today I'm going to take you through a little bit of background, what my research aim was, what my multi-parametric approach was that I took to carry out this research, we'll look at the results I found, and then what the implications of this research were. So my research aim was to understand the origin and significance of the Ice Age ponds within the wider paleoglaciological ice marginal land system of Herefordshire using a multi-parametric approach of geomorphology and geophysical techniques. So Beth touched on this already, but what are glacial land systems? Here we have an example of an ice marginal land system in Iceland. You can see on the slide that we've already got areas of ponding where the ice is melting out. And so this was an example of what it might have looked like on the ice margin. Next slide, please. So land system, the approach is really useful because we can split it down into different land system zones. So, for example, the diagram here is of the ice margin that you've just seen in the previous slide. And we can break it down into all these different sections, and then from these sections, we can work back out into the larger scale, but by looking at more specific features in different places. A key thing as well about the ice marginal land system is that it's commonly the key place for glacier permafrost interactions. Next slide, please. So what about permafrost and why is it important in Herefordshire? Next slide, please. So we know that Britain underwent periglacial conditions within the last ice age. On the map here, Hereford would have been within region 4, and interestingly, so would the area of the Pingo Ponds in Norfolk. Now, region 4 shows that there would have been permafrost in Hereford, and what's interesting is because of the short-lived ice in the short-lived glacier within Hereford, it probably would have come down over the top of the permafrost, so we would have had glacier permafrost interactions. Next slide. So to do my research, I produced a number of working hypotheses as to what the Ice Age ponds could be and how we could understand their origin. Next slide, please. I had two origins that were glacial, and I had two origins that were periglacial. So I had ice marginal decay, which is commonly seen in areas such as the Canadian High Arctic. This is where ice is melting out from moraine complexes to produce depressions and ponding. I then had glacial fluvial origin. This is the proglacial outwash plains that we see commonly in Iceland following flood events. For periglacial, you then have the two different landforms that were discussed in Norfolk. You've got the Lithausis and the Pulsars, and you've got the Pingos. Next slide, please.
Can you hold it up to your mouth?
Yeah, you can try. So I'm now going to take you through my research methods. Next slide, please. So here is a diagram of all my methods. Don't worry, we will come back to this. Initially, I did a literature review, and this produced my working hypotheses. From this, I produced modern analogues, which I knew that I could also map, and then I could compare these with the Ice Age ponds to try and work out how they formed. So initially, I applied data from Digimaps to get the LiDAR to understand the topography of the area. I had landforms from the Brick Ice project, and then I had LiDAR from Arctic DEM, which then gave me elevations of areas such as the Canadian High Arctic. Next slide, please. Something that I worked out how to do, I'm sorry to anyone who volunteered to map the ponds and did them by hand, but it turned out there was an automated method picking up where the depressions were, and it took all of about 15 minutes to do all of Hereford. So this is Penchester. You can see that the LiDAR and elevation is shown by the colour, and then the grey areas are the depressions that were picked up by the method that I applied. Now, not all of them were Ice Age ponds, but it meant that very quickly I could understand where there were enclosed depressions, and then I could go to aerial imagery and I could use maps and work out what were man-made features. Next slide, please. Moving on from that, I then did some field reconnaissance. So in May, we went out into Hereford. We drove around. I met my supervisors for the first time, despite having done 3 months of my master's. Next slide, please. And we went to lots of different places, and I met the Ice Age ponds for the first time. Next slide, please. Following this field reconnaissance, I then decided my specific sites that I would focus on to do my geophysical research. Next slide, please. I applied 2 methods here. I did resistivity surveys. This is looking at the resistivity values of below the ground. So you have a range of equipment. It's not very rain friendly and it takes a really long time. You lay out transects across the field. You have electrodes in the ground and you run a current along, and then it measures the resistivity below. Next slide, please. I also did ground penetrating radar surveys. This uses electromagnetic fields to detect structures and property changes in subsurface materials. So this is really similar to what you see if you watch Time TV, where they look at archaeology things, but we didn't find anything exciting. So you have a transmitter and a receiver on the cart, and you run the cart along the ground, and it produces profiles of what's underneath. We had an issue at Sturts with the vegetation. We had to get quite creative. Ended up making what you see here and did it by hand, and it took a really long time. Next slide, please. So what did I actually find out? So firstly, I will go through my geomorphological findings. Next slide, please. So I produced this larger map of the area. All of the black marks are what my automated approach picked up as potential ice age ponds. You've got the landform, you've got the glacial retreat pattern, and it's not really that different to the map that you can see there on the poster and what Beth's shown. It's just that it has a lot of potential ice age ponds as well. My first site that I picked to look at more detail was Sturts Nature Reserve, which you can see here. Here there were a lot more smaller rounded depressions, and you can see how flat the topography is there. Next slide, please. Then we went to Malthus Park. Now this is where it got a bit more interesting. We had these 3 really large depressions and then a number of smaller depressions dotted about. Next slide, please. Finally, we went to Kenchester, which is a lot more classic with its humping topography and intervening depressions. So you can see here, some of them are small and round, some of them are a bit more of a strange shape. Next slide, please. From my geomorphology, I then had morphometric comparisons. I produced maps for some of the outer margin of the ice cap on Basset Island, and I also did it for an ice margin in Iceland, looking at glacial kettle holes. And so here we compared the results of those 2 modern analogues with my 3 Herefordshire sites. Next slide, please. I looked at the area of the features. Here is all ice age ponds that were less than 2,000 square meters. If you include all ponds, it becomes something quite large, and it's quite hard to read data. But the one thing that you can see is there's a real similarity between the outer moraine, which is more degraded at back here, and Kenchester in the orange on the left-hand side. I also looked at the elongation ratio of the features, and again, Kenchester and Baffin were very comparable in their morphometrics. The most interesting thing to come out of my morphometrics was that none of the sites in Hereford that I looked at were comparable to the glacial fluvial kettle of Iceland. So it kind of ruled out whether they were glacial fluvial. And then it begs the question, are they actually kettle holes, which is what they've been thought for so long? Next slide, please. Now I have my near-surface investigations from my geophysics. Next slide, please. So this is the resistivity profile for Sturt salt. The blue is the least resisted and the red is more resisted. So the red areas were where the top near surface was quite dry. And the thing that you can see is there is a damp area here in the centre, and it sort of feeds down below, but there's not really much going on there other than it's all the same material and it's very clayey there, which is what we would expect from the borehole data. Next slide, please. But if you then look at the radar profile, suddenly you see a lot more going on the surface. You can see that our depression is here, and this is the damper area here. And you can see that there's nice, smooth lines, and everything's quite neat and tidy at Sturts. Next slide, please. Let's skip this because it's the same slide. Okay, now we're at Moffats Park. Here you can see that everything is a little bit more resistive. The material is different here under the surface than it is at Sturts. It's a lot sandier and there's also gravelly bits here. So at Moffats, we actually have a bit more of a rampart and a depression. And this is the pond that's here. And underneath we have this more resistive fill. But whether that is actually part of the feature or whether that is just from the difference between the really low resistivity in the pond being damp and just the dryness of the I don't know. Next slide, please. And this is the radar profile of this. And suddenly, under the ground, we have two ramparts. We have one here, we have one on the other side. And the actual depression itself, although the pond is in the centre here and it's not that deep, the actual depression underneath, you don't pick up a base to this feature until you're way down here at sort of almost about 7 meters of depth. Next slide, please. Here is Penchester. Again, we have the damp bumpy bit here, and then the dry bit to the other side. So there was a lot of clay at the surface at Penchester, and so this meant that our actual depth at Penchester was not so strong as the other sites. Next slide, please. As for the radar, you end up having almost two features with different fill, which correspond with what we see in the resistivity profile. You have a feature on the right-hand side and a feature on the left-hand side, and one has a lot more contrast in its fill than the other. But again, there was a lot of play at Penchester, and this really does upset the radar card, and it just doesn't reach the penetration that you really need. Next slide, please. So how do my results here compare with my working hypotheses that I set out at the beginning? Next slide. Well, we can see here that none of the sites match the latest video petal hole, but actually Moffats and Penchester potentially could be due to the melt out of buried ice, which produces the homogeneous viscosity that we see there. You'll see now that actually there is a third landform here that I didn't mention before. This is a thing that I came across probably in the last 6 weeks, so right at the end of writing up my thesis. And this is a possible glacial explanation for the features at Sturt, which is an iceberg gravity crater. So we know that when the lake level's lower, the icebergs come down and they eventually hit the surface. But if the lake drains and the iceberg just drops, it's never going to make the pressure required to make the ice age pods. But these gravity craters are quite significant and they are seen in Scandinavia. So it was a potential, and I didn't want to rule out a glacial origin for Sturt because I just didn't have enough data. It's possible that Moffats was a pingo, not the three large depressions that we saw there, but the small rounded ones. And then also at Sturt, my more likely origin for features was that they're calces or lithalces. Now I can't say which one they are because I don't know whether the peak was there when they formed or whether the peak formed after they were made. But we can see that there is a huge range of possible genesis for these features, and they're not just glacial or periglacial, they're actually a combination of the both. Next slide. This is just to summarise Sturt's Nature Reserve and what we found there. So they were interpreted as possible cross-mound features. The GPR and ERI profiles demonstrated depression features of around 3 metres in depth, and there was a thick sequence of clay-rich sediment. The area is characterised by a lack of hummocks, so we knew that it couldn't be the melt out of ice-cold moraine, and the kettle hole origin is definitely unlikely. Next slide, please. So Montfort Park produced 2 possible origins. One was glacial, which is that they were the melt out of ice at margin, producing humpy moraine, or that they were pingos, which would require more research to determine which one is more likely. Next slide. And finally, the Ken tester. Here it was interpreted that they would be kettle holes formed from the decay of passive ice in ice-cold moraine. But to form ice-cold moraine, you need permafrost, because you need that interaction between the glacier and permafrost to create these complexes of ice-cold moraine. So again, although it's a glacial origin, it still requires those permafrost attributes. Next slide. So what are the implications of my study? Next slide, please. 1, the use of the term kettle hole is complicated. A lot of people use kettle hole, and then you get connotations that it must be a glacial fluvial time, and that's what you see a lot in the literature. But actually, the term kettle hole is sort of thrown at any depression in a glacial landscape, but people aren't really sure why it got there, because people don't really investigate it enough. Next slide. So again, permafrost probably played a role in creating the Ice Age pods, and this was quite significant because this hadn't ever really been considered in the literature before. Next slide, please. And finally, the Ice Age pods are polygenetic, so they are not all formed by the same processes, and whether you believe that they are glacial or periglacial, they are definitely not all the same.